Today I'm going to talk to you about some of my research pushing the extreme edge of ultrafast optical science. So I want to start with the concept that the history of science is also the history of measurement. As we develop better measurement techniques, we can do better science, which lets us produce new technology, new measurements, better science. It's a feedback cycle. So it's a history of measurement, or vice versa. And to start, I'll give you an example. So this is a depiction of Galileo in 1638 trying to measure the speed of light. And in this experiment, Galileo stands on one side of a valley, and an assistant stands on the other side of a valley. Galileo will open a shutter on his lamp. When his assistant sees it, he'll open a shutter. Galileo will attempt to measure the time between opening his and seeing the light come back. And it's probably not surprising to us, he didn't do a very good job. He was only able to conclude that the speed of light is extremely rapid, or at least 10 times faster than the speed of sound. So maybe you would call an accurate measurement, but certainly with a large error bar. A couple hundred years later, Fizeau attempts to do the same thing, and he uses a more sophisticated measurement technique. He starts with a spinning gear wheel. He does something similar where he propagates light a long way across. Instead of an observer on the other hill, he has a mirror that bounces the light back, and he's able to measure light to an incredibly accurate value, accurate to 5% of our current value. And what I want to say here is that better measurement techniques lead to better science and more accurate science. Another couple hundred years in the future, we can go to maybe one of my favorite measurements, and you know someone's a physics nerd when they have a favorite measurement, and that's the LIGO observatory. So in LIGO, you've used this idea of the speed of light, and you've perfected optical interferometry to such a precise level that they're able to measure the distance between two mirrors to an accuracy of less than the width of a proton. And this has allowed us to see gravitational waves for the first time. And if you follow LIGO rumors, there's some stuff there might be some interesting stuff coming out here soon, but we'll see. And this leads to the big question of my research, and that's how does our world work on its fastest time scales and smallest spatial scales? And of course, to do that, we need to make a measurement. And my tools to make these measurements are lasers. So before I get into explaining the exact type of lasers that I use, I do want to mention that when the laser was originally developed, it was developed as a basic science question. Can we make something that does this? They had no idea the types of applications that the laser was going to be used for that we see today. And these are in health, telecommunications, manufacturing, and of course the defense and military. The laser has really become a major part of our everyday life because of this basic science initiative. And so in my work, I push the extreme of optical laser technology on two fronts that I'll talk about today. The first is temporal. I want to produce extremely fast laser pulses, so fast that the electromagnetic wave only has time to oscillate a few times while the pulse is still on. And the second front is spectral. I want to develop these ultra-fast pulses all across the optical spectrum. And so why do we need ultra-fast pulses? Well, an essential tenet of measuring a dynamic process lies in the fact that a measurement technique must be faster than the dynamics you want to measure. That's kind of a mouthful, so let me give you an example. And I'll start with something a lot of you are probably familiar with is a fidget spinner. So we, of course, have seen what fidget spinners look like, but imagine you only had access to a spinning fidget spinner, and you wanted to see what does this actually look like. Of course, if it's spinning, it blurs out like that. We can't see much about it. But if I can take an ultra-fast measurement, I can see things that we normally can't. So I bought a fidget spinner, and I got my camera, and I took pictures of it at different exposure times. And so this is 1/6 of a second. You can see we can't make any deduction about what this actually looks like. But as we speed up the shutter speed, we can start to see that we can get better and better measurements of this dynamic process. But we need a measurement technique that is faster than the process we would want to look at. Of course, I don't make a living measuring fidget spinners. I look at different processes like this. So the ultra-fast processes I want to look at start on maybe what I would call the slow side, on the nanosecond time, looking at maybe the movement of side chains and proteins, and then moving all the way down into the femtoseconds and attoseconds, where I'm really looking at internuclear dynamics and electron dynamics themselves. And these are incredibly fast timescales. So just to provide an analogy for how fast an attosecond is 10 to the minus 18 seconds, and there are as many attoseconds in 1 second as there have been seconds since the start of time. It's a truly incomprehensibly short amount of time, but using the technology of lasers, we can leverage that to actually make measurements on these timescales. Now, the other area of my research is pushing these ultra-fast sources all the way across the electromagnetic spectrum. And why do we want to do that? Well, there's a lot of reasons, but one of which is to investigate matter in different ways. So here I have a picture of my hand with a standard visible camera, and I've placed a germanium plate in front of it. And I'd take the same measurement with a thermal camera, and you can see a couple of striking differences. The first is that my hand is glowing. Our bodies are light bulbs at these wavelengths. The second is that germanium filter is now transparent or invisible. It looks very, very different in this area of the electromagnetic spectrum. Now I can go the other way and take a picture with an X-ray camera. We've all seen this. This is a picture of the first X-ray. And you can see that I learn a lot about my hand in this way too. So by using different spectrum, I can learn a lot about different things about matter. Okay, so as an example of what we want to do here, I want to apply this idea of ultrafast measurement to the nanoscale. So at the nanoscale, many of the laws of classical physics break down and quantum effects start to dominate. And by controlling the nanoscale, you can do some type of quantum engineering. And this has been around for a long time. A lot of us have heard all of the promises about nanoscale. There's a lot of really exciting stuff. And in fact, in 1959, Richard Feynman gave his now famous talk, There's Plenty of Room at the Bottom, where he presented a lot of these cool ideas of nanotechnology. But only a year later, Theodore Maiman developed the invention of the ruby laser. So why has the laser developed into all of these cool things that I showed earlier, yet nanotechnology, while still extremely exciting, has largely been confined to the lab? That's a pretty complicated question, but at least it starts with the idea that the nanoscale is really hard. So this interplay of classical dynamics and atomic dynamics, quantum mechanics really makes things hard. And so if we can understand the interactions of these nanoscales, their dynamics, maybe we can engineer them better, move them into a more commercialized setting. And so I'll give you an example that might seem simple, but like many things on the nanoscale, it turns out to be quite difficult. And that is what happens when we expose a nanoparticle to a very intense laser pulse. So these nanoparticles are small, on the order of 10 nanometers, which is a thousandth to a 10,000th the width of a human hair. And so if I bring in a strong, short laser pulse, what's going to happen? Well, we know that this strong laser pulse is going to ionize it. It's going to strip electrons off. But what happens after that is a little more ambiguous. We're not sure. We want to measure that. We want to take a picture or a snapshot of that. Now, because it's nanoscale, we need a very short optical wavelength or X-ray wavelength to resolve that. So we want to take an X-ray snapshot to measure how this matter evolves on the nanoscale and in real time. So this is an experiment will look something like this. We'll start with our nano source, and we'll shoot these nanoparticles into an experiment, and we'll hit them with a laser beam, 2 laser beams actually. The first is my ultrafast optical pulse, which will initiate my dynamics, and the second is an X-ray pulse, which will investigate my system. So these typically have a time delay between them of around 100 femtoseconds in this type of a system. And so the IR pulse will come in, it will start the process evolving. Sometime later, the X-ray will take a picture of it. So the X-ray photons will be scattered off. We'll collect them on a detector. We'll use what we measure on that detector to deduce what's happening at the nanoscale. And so by doing this experiment many thousands of times with many different delays between the IR pulse and the X-ray pulse, we can actually make a movie of what happens on the nanoscale during this process. And it looks something like this. So you have your nanoparticle, you expose it to your intense laser pulse, and the electrons are stripped off. But this is very intense and in fact strips a lot of electrons off. It leaves a very highly charged nano core left, which is very unstable. And that very rapidly transitions into a nanoplasma. The outer core of positively charged ions explodes off, and explodes off with really extreme speed, and these ions actually overtake the electron cloud, and you get a nanoplasma. And as this explosion happens, the nanoparticle core, the intact core, shrinks down. And all of this happens in less than a picosecond. It's an incredibly, incredibly fast process. But we're able to measure it by taking these ultra-fast optical snapshots. So the next thing I want to talk about is my research in the thermal. So we talked about maybe the X-ray wavelengths, how we might use this, but I'm also very interested in developing ultrafast pulses at thermal wavelengths. So we want to create short, few cycle pulses at long, long wavelengths. And there's a lot of reasons we want to do that. Many of them are scientific. We can investigate things like how ionization actually happens. We can investigate ultrafast dynamics and semi-conductors, which is incredibly relevant. But there's also quite a few strong applications. We can do molecular fingerprinting with sources like this. We can work on developing more efficient optical detectors at these wavelengths. By tuning the wavelength very exactly, you're able to find an atmospheric transmission window where you can propagate a pulse with very, very low loss for very far distances. And you can also use these for things like thermal sensor countermeasures. Because this pulse is so strong and so fast, it's able to damage a sensor in one pulse before, say, an active protection could come in. And I can personally attest how easy it is to damage a sensor with this type of a laser. Maybe to my supervisors, the detriment of my supervisor's operating budget. So I won't get into exactly how we do this, but the idea is that we start with a strong source in the visible or the near IR, and we convert those photons through several nonlinear optical processes into longer and longer wavelengths. And this does come with a hit in total power. We lose power along the way, but by doing it correctly, we can preserve the time. We can still use a very fast optical pulse. And so we've been doing a lot of work on this recently, and we've had some success, and we're able to produce long wavelength pulses with very, very short, sub 100 femtosecond pulses with central wavelengths that we can tune anywhere from about 5.5 microns out to 9,000 nanometers or 9 microns. They have incredibly large bandwidth. They have a lot of power. We're able to produce 100 microjoules or more in these pulses, which is quite impressive at these wavelengths. And with that, we can reach peak powers of more than a gigawatt. And with peak powers that strong, you can actually go in and destroy matter on a very fundamental scale. You can ionize and rip apart matter at an atomic scale, breaking the internuclear bonds, and really look at what happens there. And just to conclude, I just want to come back to my big question, is how does our world work on the fastest timescales and smallest spatial scales? Hopefully by continuing to develop this type of science, a couple hundred years from now, future scientists will look back on the way we look at Galileo and say it was a good attempt, but somewhat crude based on modern technology. Thank you.